Hey guys, hope you guys are doing well. This is going to be Monday's lesson. I was going to have it Friday, then I realized you guys had senior ditch day planned, and I have a couple more days to do it, but I'm just going to knock it out right now. It's a very short lesson. It's called the ratio and the root test. These are a pair of very powerful tests. These tests can do quite a bit. They can also tell you nothing. And so we're getting all these tests in our repertoire. We've gone through so many of them. We've gone through geometric series. We've gone through telescoping. We've gone through the P-series. We've done an integral test. We just went through and did alternating series. And now we're adding two more we're adding the ratio test, which pops up quite a bit. And then the root test pops up when you have a power that you want to get rid of. And it's going to be for a specific case. The ratio pops up a lot. The root test is very specific. And we will go over both of these. You will see the ratio test, but almost always when you have a root test, you can still do it with a ratio test. Sometimes the ratio test is much easier when you want to get rid of like I said, a specific power with a root. So here's the ratio test. The ratio test is pretty straightforward in and of itself. You need a few things. So you have a ratio test. We're taking a series that has no zero terms. There are no zero terms. I don't know why there's not a space there. That's going to bug me. But as you're plugging in each few numbers, you don't get zero. From 1 to infinity or 2 to infinity or from 0 to infinity, whatever it states. This converges absolutely if the absolute value of a sub n plus 1 over a sub n is less than 1. A sub n here means you're going to plug in n plus 1 into every n. It just started raining outside. I love that noise. Plug in n plus 1 into every n. And down here, you're just going to take the basic series and you're going to divide it. As you guys can tell, when you do this, you're going to divide sometimes two fractions. And these two fractions mean you're going to have to do some algebra. You're going to have to multiply by the reciprocal. If you get a number that's less than 1, it converges. If you get a number that's greater than 1 or infinity, it diverges. And if it's equal to 1, it tells us nothing and we have to go and do another test. It always kind of sucks when you get through a ratio test problem. You try your best on it, you get to the final answer and you get a 1 and you have to go and apply another test to it. Okay? So what we're going to do is go through a couple of these problems together. I'm going to add some more space right off the bat just because I want to make sure this is nice and organized for you guys. There are a couple of these you guys are going to do on your own. Anything that has an n factorial involved in it, I'm going to do with you guys just so you know. Let me add a page right after this. Okay, so here we go. Right here, we have to determine whether or not this integral converges or diverges. And so what we're going to do is we need to take the limit as n approaches infinity to apply the ratio test. Okay? You have to take the absolute value of a sub n plus 1 over a sub n. And what this means is we're going to go ahead and substitute in n plus 1 in for each of these n values, and it's going to give us a nice value. When we do this, we're going to have 2 to the power of n plus 1 over n plus 1 factorial. In the denominator, we're going to get 2 to the power of n over n factorial. I'm going to close my door. I don't want my dogs to run around in the rain. Just give me one moment. I'll close their doggy door. All right. So from this, as you guys can tell, we're going to have to multiply by the reciprocal of the denominator. And when we do this, what's going to end up happening is we're going to get something that looks like this. We're going to get the limit as n approaches infinity of 2 to the power of n times 2 to the power of 1, because when you have something that's written like this, these exponents, when you multiply, you add. So we're able to rewrite it. In the denominator, we're going to have to work a little bit with it. As you guys write out each of these, you guys are going to see that we have n factorial. Well, n factorial is 1 times 2 times 3 times 4 all the way out to n. N plus 1 factorial is 1 times 2 times 3 times 4 times n plus 1. And so this entire portion from here to here is just n factorial. And so we can rewrite this as n factorial times n plus 1. And this is something that's a little new. You're going to see quite a bit of it in this section. And so what we're going to do is go ahead and multiply by the reciprocal. So we're going to have n factorial over 2 to the n. What you should notice at this point is we're going to have a few things that cancel. Our 2 to the power of n cancels. Our n factorial cancels. And we're going to be left with the limit as n approaches infinity of 2 over n plus 1, which is equal to 0. What this tells us, we have a number that is less than 1. And if we have a number that's less than 1, this series converges absolutely. This series converges absolutely by the ratio test. And that is it. Okay. We're going to go through and try out the same thing here. We're going to go through and do the same exact thing. It's going to be a little involved. We're going to have a little bit of algebra, and I'm going to try my best to keep it all under track. We're going to go to the right, come back down here to the left, and so on, just so we can keep track of everything. Okay, let me go ahead and take this side off here for you. The first thing we have to do is go through and take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And what this means is we need to plug in n plus 1 into each of these terms. And so we're going to get n plus 1 to the power of 2 times 2 to the n plus 1 n plus 2 over 3 to the n plus 1. And this entire thing is going to be divided by n squared times 2 to the n plus 1 over 3 to the n. Okay, I'm going to go through and rewrite this as I go. And so let's go ahead and rewrite it first, and then we'll multiply by the reciprocal. Once again, I'm going to come all the way down here. I'm going to show arrows. When you guys are doing your AP exam on your FRQs, the grader has to be able to follow it. So if you guys are jumping all over the place, please make sure you draw an arrow, explain what you're doing, and try not to drop your limits as you guys are going, okay? So what we're going to have here is the limit as n approaches infinity of n plus 1 to the power of 2 times 2 to the n times 2 to the power of 2. Once again, with exponentials, if you multiply, it's the same as adding. We're able to break it apart. Same thing in the denominator. We're going to have 3 to the power of n times 3 divided by, or we can multiply by the reciprocal if you guys are comfortable with it. We're going to take and flip this right here. We're going to have 3 to the n over n squared times 2 to the n. And this 2 to the n plus 1 can be rewritten as 2 to the n times 2 to the 1. The 2 to the 1 doesn't really matter. Okay. What we're going to do is go through and cancel quite a few things before we go through and write out the next part. We're going to go through and cancel quite a lot, actually. We're going to cancel 2 to the n. We're going to cancel 3 to the n. We're going to cancel a 2. And we're going to be left with 2 times n plus 1 squared over 3n squared. If this number comes out and is less than 1, then the series converges by the ratio test. If it's greater than 1, it does not. What you guys are going to see from here is, if you plug this in, we're going to get infinity over infinity. So we're going to have to go do L'Hopital's rule 2 times. So let's go ahead and do L'Hopital's rule. And so we're going to get the limit as n approaches infinity of 2 times 2n plus 1. I just did power rule over 6n. Okay. Then we're going to go through and do L'Hopital's rule once again. We're going to do L'Hop's rule once again. We're going to get the limit as n approaches infinity of 4 times 1 over 6 times 1, which is going to leave us with 4 over 6, or 2/3. This is less than 1, so this implies that the series converges by the ratio test. Okay, this converges. Let's go ahead and write it out. When you guys write it on your AP exam, you're going to want to explain yourself to the best of your ability. And so we have to go through and explain why. Since the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, then the series converges by the ratio test. And that is all. Once again, it's a little bit involved. All of the ones that have n plus 1 involved in it, I will do with you guys. The ones that don't, I'm going to let you guys go ahead and do. So this next one right here, when we go down, did I fit that all on that page? I am impressed. Right here, this problem, I'm going to leave to you. This is going to be a your turn problem. I'm going to leave that problem to you. We're going to go and do the one with n factorial off to the left-hand side. This one's going to be a little involved because we have n to the power of n. And so what we need to do in a problem like this, whenever I have n to the power of n, I want to apply the ratio test. The ratio test states that if you take the limit as n approaches infinity of a sub n plus 1 over a sub n, and if this value is less than 1, then our series converges absolutely. If it is greater than 1 or equal to 1, if it's greater than 1, it diverges. If it's equal to 1, it's inconclusive, and we have to do a little bit more. This problem is quite a bit involved, so let's go through and see what happens. We're going to go plug in n plus 1 into every value of n. So we're going to get n plus 1 to the power of n plus 1 over n plus 1 factorial, all over n to the power of n over n factorial. There are a lot of n's in this. That's not going to stop us. We're going to go through and we're going to multiply by the reciprocal of this. We're going to go through and multiply by the reciprocal, and we're going to get the limit as n approaches infinity of n plus 1 to the power of n times n plus 1. I don't know if this is going to help us if we rewrite it this way, n plus 1, over n plus 1 times n factorial. We're able to rewrite n plus 1 factorial as n plus 1 times n factorial, just like we did right up here and we talked about prior. Okay. And then we're going to multiply this by the reciprocal, which is going to be n factorial over n to the power of n. What you guys are going to see is we have quite a few things that are going to cancel. Our n plus 1s cancel. Our n factorial cancels. And then we're going to be left with this monstrosity where we have n, the limit as n approaches infinity, of n plus 1 to the power of n over n to the power of n. Okay? When we do this type of problem, we're going to notice something a little funky. You guys are going to see it, and you're going to go, okay, where did this come from? You look closely, both of these have the same exponent. And so we're able to write it as 1 exponential. We're able to write this as y equals the limit as n approaches infinity of n plus 1 over n, quantity to the power of n. Once again, since they both have the same power, we're able to rewrite it as such. You might recognize this from one of our earlier sessions where we had to go through and figure out what the sum was from 1 to infinity of 1 plus 1 over n to the power of n. When we had to find this sum from n equals 1 to infinity, we had to do the same sort of thing. Once again, this is not what we're using for it, but it's going to be the same sort of principle. We can't solve this when we're going to have a number to the power of infinity. In this case, we're going to have infinity divided by infinity to the power of infinity. And that's going to be an indeterminate form. We want to do L'Hopital's rule, but this exponential is going to keep us from doing so. So what we have to do for this problem specifically is we're going to go through and we're going to take the ln of each side of our equation. And what this allows us to do is bring down n into the front. And so we're going to be left with is ln of y equals the limit as n approaches infinity of n times ln of n plus 1 over n. Okay. When we plug in infinity, if we take each of these, this is going to approach infinity. This is going to approach infinity over infinity. And we're going to run into some issues. And so to actually rewrite this, you might recognize this again when we have n plus 1 over n. We can actually rewrite this right here as 1 plus 1 over n. It's going to end up being a very similar problem. This, when we plug this in, we're going to get infinity times the ln of 1 plus 0. Okay? And so we're going to run into a few issues here. Let's go ahead and try it out. We're going to get ln of y equals this. Okay. So when we do this, we might actually be able to get away with this problem. Let's try it. We're going to have ln of y equals infinity times ln of 1 plus 1 over infinity, which is going to approach 0. This is going to be 0. ln of 1 is 0, so we get infinity times 0, which is going to be an indeterminate form. So we actually have to go through and rewrite it. And we're going to have to write this as ln of 1 plus 1 over n over 1 over n. Okay? We're going to have to go through and apply L'Hopital's rule. So let's go ahead and try this out. Let's try to keep track of it as best we can. So we're going to have ln of y equals the limit as n approaches infinity of 1 plus 1 over n. We know that this is the same as n to the power of negative 1. So the derivative is going to be negative 1 n to the negative 2. Over, this over here is also that negative 1. So we're going to get negative 1 over n to the negative 2. And we can make this a fraction if we felt like it. We can put this over 1 and then multiply by the reciprocal. So we're going to get ln of y equals the limit as n approaches infinity of negative 1 over n to the negative 2 over 1 plus 1 over n times the reciprocal of the denominator, which is 1 over negative 1 n to the negative 2. All of this is going to cancel, and we're going to be left with ln of y equals the limit as n approaches infinity of 1 over 1 plus 1 over n. And you guys are going to see that this right here is going to approach what exactly? This is going to approach well, actually, if I'm sorry, I have to take that limit, my bad. And so we're going to have 1 over 1 plus 0. So we're going to get ln of y equals 1. which if we didn't have the ln of 1, if we didn't have the ln of y on the left-hand side, we'd run into an issue. Because if you get 1, your entire thing comes inconclusive, and then you have to apply another test to it. What we don't see here is we have to go through and solve for y. So we're going to take e to the power of, and we're going to be left with y equals e. Okay? Now, there are only a few sums that you guys are going to see quite often. You may or may not see one on your test. This was a lot of work. This right here, this sum, is equal to e. This sum approximates e, 2.718, and so on. If you see it, it's going to give you e. And so right off the bat, we should have seen that. But we didn't, and that's completely okay. We didn't see it at this point. I should have saw it right here. And so we went through the full derivation once again. This quite literally would give you, if you divide each term by n here, you would have had 1 plus 1 over n to the power of n. And that would have told us right away that that's e. And so we got y equals e. This is larger than 1. So you'd say since the limit as n approaches infinity of a sub n plus 1 over a sub n, the absolute value of, is greater than 1, the series is divergent or diverges. Okay. What I'd like you guys to do is please, after all of that, go try out this next problem. Go ahead and please try this out for us. You're going to be working with some square roots. It shouldn't be too bad. I would rewrite them as 1/2 powers when you do it. Don't forget to take the absolute value when you write it out. The negative 1 to the power of n will go away when you're doing this problem. All right. The next part, this is called the root test. The root test is nice when you want to take the nth root of something. When is this nice? When you have something like the quantity of a to the power of 2. The root test is going to cancel it out when you go through and you take something like a to the power of n, and you want to get rid of that exponential. You're able to go through and get rid of it. And then if you take that sum, you're able to find if it's less than 1, then it converges. If it's greater than 1, it diverges. If it gives you 1, then it's inconclusive. Just like the last test, they're very similar to one another. Here's a prime example as to why you might want to use the root test. Okay. First off, I see this e to the power of 2n. I don't like that. I know I can rewrite this as the sum as n goes from 1 to infinity of e to the power of, this is n squared, because that's power of a power rule, and this is n to the power of n. I'm going to go through and try out the ratio test, or the root test for it. So we're going to go and try out the root test. And what this states is just as follows, right? We're able to go through, and we're trying to prove that this is less than 1. Let me go ahead and copy and paste this right here below. So what are we doing? We're taking the nth root. In this case, I'm going to rewrite this now that I see what I'm looking at. I'm going to take e to the power of 2, quantity to the power of n. And when I see I have both of these to the power of n, this is going to allow me to get rid of that power of n. So I'm going to take the limit as n approaches infinity of e to the power of 2, quantity to the power of n, over n to the power of n. And I'm going to take the nth root of this entire thing. Okay? When I take this nth root, what's going to end up happening is I know when I have a square root, I'm able to take the square root of the top and the bottom of a fraction. So I'm able to rewrite this as the limit as n approaches infinity of the nth root of e to the power of 2 to the power of n over, I don't know why I put a 2 here. This is supposed to be to the power of n. This is n to the power of n. I am sorry for that. And we're going to have the nth root of n to the power of n. And so what ends up happening is our root cancels with our nth power. Our root cancels with our nth power, and now we're left with the limit as n approaches infinity of e to the power of 2 over n. And as you guys know, this is going to approach 0. There's no variable in the numerator. And so this is going to be less than 1. It follows our rule. And what this means is it's going to converge absolutely. And we're going to write something along the lines of, since the limit as x approaches infinity of the nth root of the absolute value of a sub n is less than 1, then the series converges absolutely. Okay? This is what you guys are going to be working on Monday, and then you guys are going to start on the practice problems for it. I'm going to be working on a video going over some of the practice problems from the section. I'd like you guys to try your best on them. Hopefully me doing a video at 10:30 at night wasn't too bad. I'm falling asleep, but I hope you guys have a great day and good luck. Hopefully the baby's born tomorrow. Have a good one. Bye.